Hi guys, today we're going to talk about some models that we can use to find out more information about exponential functions. So I'm starting on page 18 today, and our first model that we're going to look at is about how information spreads. So this says, Susanna heard some exciting news about a well-known celebrity. Within a day, she told 4 friends who hadn't heard the news yet. By the next day, each of those 4 friends told 4 other people who also hadn't heard the news. By the next day, each of those people told 4 more, and so on. So you learn the news, you tell 4 people, and then the next day, everybody who's learned the news tells 4 people, and the next day, everybody who's just learned the news tells 4 people. And that's sort of our pattern that happens here. So assume the rumor continues to spread in this manner. Let n be the function that assigns d the number of people who heard the rumor on the dth day. Write an expression for n of d. So n of d would be how many number of people have heard this expression after d days. So we started with 1 person. Our initial amount is 1, and our growth factor is 4. So 1 times 4 to the d would be our exponential function to model this situation. B says, on which day will at least 100,000 people hear the rumor for the first time? So this is like our y, or our n number. So I'm going to put this in the y spot, or the n of d spot, because that's the number of people that we're looking at hearing this rumor. What I want to find is what day do this many people hear the rumor? So we're trying to solve for d. I'm going to actually use my calculator to help me solve this. I'm going to take a look at a graph of this function. Let me bring up my calculator, and I'm going to graph here. So I'm going to start by graphing this 100,000. Now I can't see that on here because my y value only goes up to a little below 7. So I'll have to do some adjusting here in a minute. But before I do, I want to add the exponential part of this function. So that would be 1 times 4 to the x. Since I'm giving this direction to my calculator, I'm using x instead of d. And there's the exponential part. And then I'm going to menu. There's my zoom. There it is. Zoom. I'm going to try a zoom fit. Just my zoom here so I can see what's going on. And there I can see that intersection. That's going to give me the day that I hit 100,000 people. So I'm going to look for that intersection. So menu, analyze graph, intersection. I'll click on either side of that intersection, and that gives me my point. So I've got 8.3 as my x value. So partway through the 8th day, or 8 and some into the 9th day, I guess we should say. We've got the whole 8th day there into the 9th day. So I'm going to say approximately 9 days. For C, it says how many people would hear the rumor for the first time on the 20th day? This time, I know the value for D, so I'm going to plug that into my function. What we're trying to find is that number of people. So I'm going to go back to my calculator here. And this time, I just want to do a quick calculation. So this would be 4 to the 20th power. And we get a really large number here. 1099516277776. Now that I've copied that down, put away my calculator. So this would be, there's 100, 100,000, 100 million, 100 billion, a trillion, roughly 1 trillion people. So on the 20th day, 1 trillion people will hear this information for the first time. D asks if that is realistic. Our whole world population right now is a little over 7 billion, I believe. So I would say that this answer is probably not realistic. that would be more than the world population. So that is probably not a realistic answer. Anytime we're talking about a function with a context, there will likely be limitations to how we can use that function. So after 20 days in real life, maybe we don't care so much about this information and the rate of this sort of spread of this rumor may have slowed or even stopped. We're certainly limited by the world population for how many people can learn this information. So then E asks us, what would be an appropriate domain and range for this scenario? For domain, that would be my number of days that this rumor has spread. So we're going to have to look at some D value that gives me a population less than our world population. So if we pull up our graph, and let's say that let's see if I can put this away. Let's say that our world population, let's say that our world population is, we'll say 7 billion. So 700. Here, we want to graph trace here. Oops. Okay, so trace, graph trace. Okay, we're going to search for an X value of 7 billion, and we're on the wrong line. Let me see if I can switch us over here. Okay. So let's go ahead and get rid of that. Now let's try a graph trace. 7,000, 70,000. That should be about what we're looking for. Undefined. Okay, here. Let's pull up our table. That might be an easier route to go. So if we pull up our table, there we go. This is going to be easier. And we're looking at the number of people we're going to have for this specific day. Okay, so here at 7 days, we've got 16,000. At 8 days, we've got 65,000. 9 days, that looks like 262,000. And as we keep increasing, we know by the 20th day, we've gone way too far. So we're looking at what would be reasonable. So this 1 point is because we're in scientific notation. If I click on that number or hover over it, it gives me that sort of the rest of that number there. So we're looking at probably something more in the maybe 13-day range, 10 to 12 days, something like that, based on those Y values, because again, this would be when I'm looking at the whole population. So I want a D that's going to be greater than or equal to 0. Equal to 0 because we have that initial amount from that, what we're going to call the 0th day when that first person learns. And then probably something less than, we'll say 12 days. For our range, that's going to be our number of people. And so we know we're starting with 1 person. And then we've got to be less than, I'm just going to write the world population here. So what we're going to see is after about a week and a half, after 2 weeks, this model doesn't fit our spread of our rumor anymore. Let's take a look now at page 19. We've got another example that we're going to look at. This is an example that a lot of us would probably care about, and it's how to grow your money. So our context here is that on January 1st, 2010, Janice put $450 in a savings account that pays 4.2% interest once at the end of the year. We could say compounded annually would be another way to phrase that. Write an equation that can be used to calculate the amount of money that Janice has in her account in terms of N, the number of times the interest has been paid on the account. So if you take discrete math, we're going to do a whole chapter on problems like this, things like this. So we're starting with our initial amount, 450. And then this guy works a little bit differently. 1 plus, I have a rate this time. So I'm going to use that 1 plus R model. 4.2% written as a decimal would be 0.042 to the n for the number of times that we compound this money or collect interest, which we know will be once a year. So for part B, we want to know how much money will we have in January 2014? Well, we're starting in January 2010. So this is 4 years later. So I'm going to plug in 4 for my exponent. So 450 times 1 plus 0.042 to the 4th power. I'm going to bring up my calculator again so I can do a quick computation. So I want my scratch pad back here. So this would be 450 times 1.042 to the 4th power. So we get 530 point. This gives me 498. Since this is money, we want to round to the nearest penny. So 0.49 with the 8 is going to round up to 50 cents. So $530.50. That's how much total she'll have in her account in January of 2014. Part C, I'm going to know, when will she have $1,000 in the account? How long will it take her to get that amount of money? So this is a Y or a B value. And I want to know what's the N value. I'm going to go back to my calculator and I'm going to use the graph again. So I'm going to make a new document here. And we'll start the same way we did on the last problem. I'm going to graph that Y value of 1,000. And then I'm going to graph that function, 450 times 1.042 to the X. Since I'm typing this in my calculator for a graph, make sure I use X and not the variable N that we use to write our equation. And then menu, zoom, let's try zoom fit again. Not the best picture, so menu, zoom. Let's try zooming out here a little bit. There we go. Do one more. So again, what I want is the intersection between these two graphs. So menu, analyze the graph, intersection. And we get 19.4. So when will the account reach $1,000? When N is 19.4 after 19.4 years. Since we only compound once at, I believe, the end of every year, after the end of the 19th year, I won't have enough money in my account, so I'll actually have to go to that 20th year. And so when, after 20 years, or since I know we started in 2010 plus 20 years would be in 2030. And then finally here, this is the rule of 70 states that an account will double in approximately 70 over R years. Confirm or disprove this rule for Janice's account. So for this particular rule, we don't need to change R to a decimal. We're going to leave it as that percent. So 70 over 4.2. 70 divided by 4.2. Let me go back to my calculator here. And we'll just pull up our scratch pad. 70 divided by 4.2 gives us 16.667. So this says in approximately 17 years. This doesn't match what we found in part C, right? We had 20 years, but we also went a little over double. So if I want my money to double, then I need to look at 450 plus 450, that would be 900. So we'll have to look at our graph again and figure out what's our end there. Do we get about 17 years? The other option is we take 17 and plug it in for n here. But since that's an approximation, I'm going to go ahead and go to the graph to see just how close we got. So let's go back to our current graph and let's graph 900. That would be a double of our money. So at 900, I want to know what's the intersection here with my red exponential graph and my black linear graph. So menu, analyze, intersection between these two graphs. There's our point there, 16.8. So we're looking at, again, approximately 17 years for our money to double. So yeah, this looks about right. We were off a little bit on that decimal place, but it's going to take that 17th year in order for me to be able to hit that 900 mark in either case. So yes, that rule of 70 looks like it works. That's it for our notes for today, and I will see you in class.